This is where I live, Twin Hills, Kansas.
When you grew up there?
Now, I grew up in Omaha, went to school in Lincoln and Boulder, but I've spent 39 years in Manhattan, Kansas. Okay, so I handed out these, I think, rather difficult conceptual pictures here with regard to how the phasors are acting across the slit. And there were regions of size 2 pi over q prime, remember that? In which all the phasors have done a total loop, and so they're summing up to 0. And it's rather interesting to think, apparently, so the camera gets over here as well, Ethan? Mm-hmm. Yeah. So let's remember that in the slit, I'll draw a physical slit now. Here's the obstacle, here's the slit going from A to minus A. There are these regions whose size is 2 pi over q prime, right? In which the phasors, right, the sum, can't see that, can you? In which the sum of the fields is 0. And although non-uniquely, we can center these q prime regions on the slit, that leaves very often just a little bit on the edge where the phasors aren't adding up to 0, and that's given us some finite field out in the far field. So here we go, clear out here, and we're getting a diffraction pattern. Since I'm dealing with the field, I won't square the sinc function. Here it is. And this particular arrangement might be right out here, some finite amount of field. And of course, every time as we continue to change the angle, all right, remember q prime is k sine of the angle, right? 2 pi over lambda, sine of the angle. So as we continue to crank this angle around, the q regions change, and every once in a while they totally fill up the slit and we go through a minimum. So that's the concepts that we got. Now, also on one of the diagrams I handed out, I drew the slit profile. We did this last time, so here's now the transmission profile, T of x for the slit. And I've got all the phasors in here, right, working my way across the slit. Something like that, okay? But I'm going to take advantage of the fact that while over a span of 2 pi over q prime, remember that has units of length, right? Inverse q prime is inverse units of length. Notice there's a smaller region where I'm pretty much in phase. And I'm going to arbitrarily make that distance 1 over q prime. Let's remember this distance for the particular angle I picked is 2 pi over q prime, a factor of 6, bigger, right? So I'm taking about a sixth of this region, and any sixth I sorta, right? Sorta have the E phasors in phase, right about there. And I'm going to call those Q regions, not 2 pi over Q regions. Okay? And I'm going to try to do an analysis with that. And this takes me to something that we call the Q-space analysis, okay? Or the scaling analysis, because it involves scales, as you'll see as I start to work on this thing. So, you ready for me to go? You okay if I take these smaller regions, say everybody's in phase in the smaller region? All right, let's do it. So the idea is we're going to have regions, Q regions, with size 1 over Q, in which the phasors for the field are in phase. So since the phasors are in phase with this coherent addition, we're going to get a lot of intensity. Now I'm going to apply these Q regions to our system of scatterers. So any object, any particle that's going to scatter light. Now I might add, this can be extended to the whole system, the whole aerosol or the whole colloid. It's up to you to define. I'll say that a little more. This might be a 10 micron grain of sand blown off the Sahara Desert. We're going to split it up. We're going to break it up into a system of scatterers. Remember, we're putting in little point-like scatterers uniformly in here. That would be one application of what I'm about to do. Another application would be that this is the entire aerosol. And then I'll do a different scale and consider each one of these as one of the particles in the aerosol and look at it from that point of view too. A lot of it depends upon length scales, which we control through Q, which we control through the angle, right? So if we have very small Q, we could have very large inverse Q that would handle the whole aerosol, right? It might be a millimeter. Now that's hard to do. You're going to have to get to very small angles using the wavelength of light at being a half a micron or something like that. On the other hand, more normally at angles measured in degrees and so on, these inverse Q regions are on the order of microns or something like that. And then we're looking at a single particle. So having said that, you know, you could read some papers that I've published to get into that point of view. From now on, we're just going to concentrate on how single particles scatter. This blob here represents a single particle of some sort. We've broken it up into a system of scatterers. And now I'm going to put one of my Q regions on there, right here. Here's a Q region. Its radius is inverse Q, so its diameter is twice that. The factor of 2 isn't particularly important because I've already been making some approximations that all the phasors are exactly in phase. They're not quite. But let's just use the factor of Q, of 2. Actually, as I think about it, let's drop the factor of 2 just so I don't confuse anybody. Let's just do that. 2's and factors of 2's won't be important. And now what I'm going to do is say to myself, okay, the number of little point scatterers in here is n sub q. So in this Q region, I have n sub q point scatterers. Right? So the field from that Q region is proportional to n sub q. Right? Now let me ask you, what's the scattered intensity proportional to? The square of that. Very good. Now, I want to move this Q region around. Just with this, remember with the slit, we had a whole series of 2 pi over Q regions. Let's throw a whole bunch of Q regions across this. So I'm going to put a second one over here. Okay, it's the same size, so I'm going to do the same argument. But let's remember from the slit, once we start getting bigger than inverse Q, we start finding phasors that are out of phase with the ones that are next door. Remember that? Okay, so if we start getting phasors that are out of phase, then we can't come up with the field directly proportional between these two. We can't add these in phase with those. We have to account for that fact that they're out of phase. So what we're going to do is say, okay, instead of adding fields, we'll add intensities. Let's suppose we have another number, n sub q, which is the number, perhaps I should say the total number, of Q regions. All right? Then I would combine these two and I would say that the total scattering from the particle is proportional to the number of Q regions times the intensity for each Q region. Now, you think about this a little bit. You probably recall from elementary physics that when you're doing things like interference, you have to add the waves, right? You have to add the amplitudes, and then you square the amplitude to get the intensity. And that's because there'll be an in-phaseness or an out-of-phaseness that's going on. You've got to pay attention to the phase of the field. And yet, on the other hand, when you're in this room, if you turn on one light bulb, you get a certain intensity, and when you turn on a second light bulb, you don't get 4 times the intensity, you get twice the intensity. And the reason why is those light bulbs are out of phase with each other. It's that sort of idea that I'm doing here. All the points within the Q region are in phase. So the field is proportional to the size of the Q region, and so I got to square it to get to the intensity. On the other hand, this is one light bulb in the room, and that's another light bulb in the room. You see it? And they got nothing to do with each other. They're out of phase with respect, or they're randomly related to each other. If they're out of phase, they'd cancel each other. But I'm not looking at phase anymore. These are independent light bulbs, is one way to explain this. So that's how I come up with this relationship. There's another lesson that we have to remember from this single slit, and that's why I spent so much time with the single slit last time, to get this point of view across. Remember, the 2 pi over Q regions in the interior of the slit gave us how much to the total intensity in the scattering, in the diffraction pattern? Gave us nothing. It was only at the edges that we started to get some contribution, right? I just erased that, didn't I? How much did these guys in the interior give us to the total diffraction pattern? Nothing. Nothing. Where do we get something? See it? Only on the edges.
And that's just because the path, if I take the Q region, I add all the path length differences, they're all just cancel each other out. So just because one of them is partially empty, there's just some left over.
There's a couple reasons. I mean, you can look at it in a number of different ways. One is from the analogy with the single slit, that we saw that the contributions from the center of the slit there were contributions, but these all added up to nothing. These all added up. I'm doing phasers now, rotating around. And it's only when we got to the end when we couldn't do a full circle of phasers that we get something finite. So that's one way to look at what I just said. Another way to look at this is that uniform systems don't scatter light. It's fluctuations in density that scatter light. So, for instance, the sky is blue for two reasons. One, Rayleigh scattering, but two, because it scatters in the first place. Why does it scatter in the first place? Because if you look at the density of the air over scales of microns, it's not a constant density of, 1.3 milligrams per cubic centimeter. It fluctuates a little bit. If it was a constant density, the sky would be black. It would not scatter light. Fluctuations scatter light. Where are the fluctuations in the interior of the particle? Remember, I made a big deal about saying I'm going to put these little black dots in uniformly? That's why I did it. I don't want them scattering light. And if it's a grain of sand, and if it's a uniform grain of sand, there are no fluctuations. Where's the fluctuations? On the edge. Because here I got sand and here I ain't got sand. There's a change, and that's why it scatters light. So there's a lot of conceptual stuff in here, certainly. Question is, does this work? Well, sure it works, or I wouldn't be bothering to set the whole doggone thing up. So I'm going to show you how it works next, if you're ready to go, right? If I've wrestled you into submission that this will work.
Sorry, I have a question.
Yeah, I hope it wasn't whatever I erased.
No, not there. But the total intensity is proportional to the number of Q regions
Yeah.
with like NQ squared. So those are contributed by the surface?
Yeah, those will be the ones on the surface that are active. Yeah, so I'm going to have to pay attention to that when I set this up. So what I'm going to apply this to a spherical geometry, all right? And I'm going to see what I get, and then I'm going to ask you if you did your homework and did that integral for the diffraction from a sphere yesterday. And even if you didn't, I'll end up writing it on the board and we'll compare, okay? So here we go. Let's take a sphere. Let's fill it uniformly with point scatters, etc., etc. All right, let's put a Q region on it. I guess I'm switching my colors around here a little bit. So Q regions like this are contributing nothing, right? They're interior. It's only the ones on the surface, right? Okay, so here we go, putting things in here. So how many scatterers are inside of a Q region? Well, it's going to be proportional to the size of a Q region, right? How big is the Q region?
The inverse of Q.
Yep, it's the inverse of Q. I'm going to leave the prime off for a while. I'm getting tired of writing primes, and of course I don't want to waste all this ink writing those primes as well. And let's see, but this is a three-dimensional sphere, right? So by golly, these are three-dimensional Q regions, correct? So we ought to cube this, because it's a volume. Okay, how many Q regions are active? Well, we've already agreed that the ones in the interior aren't kicking it in, right? We've just got a whole bunch of them on the surface, correct? We better give a radius to this thing. So we got a sphere radius capital R, and let's remember the radius of these guys are the diameter. Again, I'm dropping factors of 2, but these are cutting little circles on the surface, right? And so it seems to me a ratio of areas, right? So the number of Q regions is the area of the sphere divided by the area, the cross-sectional area of the Q region, which is its length squared as well. Okay, and then we claim the intensity is that. So let's see what we get. Well, I'm sorry. These are all proportionalities. Like so. So here we go. The intensity is R squared Q to the minus 1 squared times this cubed. So I've got R squared, and I've got this, it's sort of a double Q here, right? This becomes a Q squared, and this is a Q to the minus 6, so I get R squared Q to the minus 4. Okay. Now, is that correct? Well, we could look at the analytical solution, but what if we generalize this? I'll use blue. What if this was a one-dimensional sphere? Right? What would change? What's the volume of a one-dimensional sphere? Right? How would this change? Yeah. How many of these would there be? On a slit, there's only 2. Doesn't scale with the length, right? There's only 2. Notice there's no scale. What's the intensity? Well, again, proportional to NQ, NQ squared, little nq, big NQ. That's 2 times, that would be Q to the minus 2, wouldn't it? So we get, remember? That was what the sinc function was for the single slit, right? What if the dimensionality of this object was dm? The mass fractal dimension. Okay? There's death out there. Are you know what I'm talking about? Have you heard of, who's heard of fractals? Okay, you probably know that the mass in a fractal increases with the size of the fractal, but not as the cubic power, like most things, but with a fractal dimension of 1.8 in many cases, right? That's the mass fractal dimension. Some objects also have surface fractal dimensions. So you might double the size of some blob of stuff with a very rough exterior, and the area does not get 4 times bigger. It gets 2 to some power bigger, ds, and maybe it gets 4.7 times bigger or something like that. So we can generalize the concept of dimensions to non-integer values. I haven't done this derivation in a while, so I'm sticking my neck out. Let's think about it together. The number of little point scatters in these Q regions, seems to me that doesn't have anything to do with the mass fractal dimension. The surface fractal dimension, on the other hand, would get involved. I've got a problem. Let's see. Right, I'm trying to generalize this to any dimension. Let's see. The number of Q regions across the surface. Let's just try this. This may not work, but what the heck. So if we go to reds, I'm thinking that the number of Q regions, the number of scatters in a given Q region would still be Q to the minus 3. But the number of Q regions, little n, would depend upon the surface area, right? Which now is in some manner rather rough. So we would have a surface. Remember, this was the ratio of the area of the sphere to the cookie cutter area of the disk that these Q regions create. So if I put a different dimensionality here than there, that's not going to work, I don't think. Let's try it. R to the ds, the surface fractal dimension, all over Q to the minus 1 squared.
Should it be ds then on the bottom too, just because you want dimensionless?
That's what I'm worried about. I'm getting the wrong dimension.
And shouldn't NQ go to dm?
Yeah. Why is NQ minus 3?
Well, I think it should go to dm too, but I don't know why. I can't justify it because my Q regions are still Euclidean.
It shouldn't go to DM.
Yeah, the number of them
Number is
should
not
go.
3. Number is D. Number is minus 1.
No, but the Q regions, they're spherical. Why should
Yeah,
Q regions are spheres.
But the number of them that are occupied.
It's about how many are in that Q region. So if that's not
Is volume of the region or surface of the region over surface of the Q regions, they're still spherical.
Q regions are spherical, but things inside them are not uniform. So that isn't that what DM would take care of? Because if it was a sphere, the entire thing was a sphere, then you have uniform distribution. So any volume would have the same amount of stuff in it. So you can just say Q inverse to the power 3. But if it's a fractal, let's say, then even though the Q region is a sphere, the number of scatters in the Q region is not the same. It's not basically going as a flip-flop.
So that's basically the feed into.
I've got an idea. Let's forget fractals. Let's just say mass and scaling dimensions. Okay? And we had 3 examples. So a sphere has a mass dimension of 3 and a surface dimension of 2. A disk has a mass dimension of 2 and a surface dimension of 1, right? And notice when I did the Q regions, I put them in the same type of geometric space, right? So when I didn't do the disk, unfortunately. Let's do the disk and then let's generalize it. The slit is a little deceptive because there's only 2 Q regions. So let's do the disk and pay attention to what happens, and I think that's going to solve our problem. So let's label this disk, and what the heck, I can draw it again. It's going to look the same as the sphere. But now when I go to calculate n sub q, I'm just thinking 2 dimensions, right? This sphere, this is no longer a sphere, it's a disk as well. So the Q region is a disk too, right? So I have to worry about the area of the disk, correct? Right? Then the number of Q regions, well now this is linear, correct? So I'm comparing this diameter, this segment of length compared to the circumference, correct? Notice the one-dimensionality that's coming in. So the number of Q regions is just the total circumference, which of course is proportional to r, divided by the size of the Q region. So then when I put these together for our intensity, let's see, I'm going to have to leave room for my red over here eventually. So I get R, and I'm going to bring this up, times Q. I'm going to square this. Ooh, I got to square this, right? It's already squared once. When I square it again, I'll get a 4th power, correct? Minus 4, so I end up with R, Q to the minus 3, which in fact is correct. Okay. Now we boldly go, not so much thinking fractal and roughness and all that sort of stuff, but just to generalize dimensions of dm and ds, and we can see that we're going to get just like we did here, right? Cubed, squared, 1 over q to the dm. Correct? It was 3 and 2, and it was even 1. And when we do n of q, I'm gonna forget about this. Well, I guess I could do an r to the ds. Yeah, well, actually it's a ratio, isn't it, right? Both were squared here, the surface dimension. Both were to the 1st power. So let's do the quantity, q to the minus 1 to the ds. There it is, reasoning by analogy. And now when we put it all together, let's see, it comes up to a plus ds. And then up here, I'm going to have to square it. Q to the minus 2 dm, and running rapidly out of room, right down at the bottom, we get r to the ds Q, I'm going to write it as minus 2dm minus ds. And that is the grand result.
So does normally ds smaller than dm by 1?
I don't know. So he asks, is ds always 1 less than dm? I don't know. I think it is for geometric objects. And I also know for fractals, dm equals ds. Because every particle is on the surface to a good approximation. Let's take stock in what we've done now. All right? We have a general formula, and in fact it works, right? 1 and so here's the surface of the disk, correct? Here's the surface of the sphere. Here's the combination of 3 and 2 and 2 and 1, right? So these are generalized. Let's bring them in now. This is Porad's law. Right? The man famous for all his work on small angle X-ray scattering, where diffraction dominates. And we've got two important quantities here. We've got the right power law with Q, and we've got the right surface dependence. Remember when I alluded to the fact with the slit last time that it's only the edge, only the surface that kicks in out in this power law regime. So that's the scaling analysis.
So this is all Q regions that are smaller than the object.
Wonderful question.
Can you get the minimums and all that stuff out of it?
See, I could pretend like I feigned confusion 15 minutes ago to get everybody to think about the problem. I could claim that I paid Will off to ask this question right now. None of which is true. I was confused for a while, I'll confess. Because I had a meeting at 8, oral defense at 9, and then I had to stay after the oral, and I didn't have time to prepare for this lecture. I was so nervous about that. See, I get nervous too, okay? So there are true confessions of an old scientist. But great question nevertheless. Let's think about this together. Okay, when Q gets really small, what happens to inverse Q? It's humongous, right? And so you got some particles sitting here, and it can't even see the shape. That's an important fact. But people are worried about just spheres or irregularly shaped particles. But with small q, you got big inverse Q, and it don't matter no more. And now your Q region's this big, right? And the particles like this, and son of a gun, all those phasors are in phase, aren't they? Right? And so the scattering is going to be, you got only one Q region now, right? Here, again, this is probably worth boxing this formula, because we've been using it. All right? So with this very, very large inverse Q, we got one of these, and there's all the point scatters in the particle. That's the volume. So, ready to erase? What this scaling analysis gives us is a conceptual point of view. This is not new physics. People knew all this stuff. When you did the Fourier transform of the sphere, I hope last night or sometime like that, you saw this come out. But it gives us a concept of what's going on. And this scaling analysis yields the following result. that the scattering, the diffraction, the intensity is going to be constant as long as Q is small, and it's finally going to curve over when it starts detecting the size of the particle, right? So if I'm plotting this versus Q, right about here is inverse the size of the particle. And then it's going to fall off with a power law, and let's remember, this is going to be proportional to the volume squared, right? Then it's going to fall off with a power law, Q to the minus 2dm minus ds times what? The surface area. So this simple analysis yields these very important results.
But you can still get where it's zero and stuff like that, because a full Q region means nil, nothing. So you at least get the first minimum, right? Because
Yep. Yep. So we could take this further and recognize that if we just match sizes properly, get a Q region right at the right size, it's going to dip down in here. I haven't tried that. I don't think it quite works. I mean, with one dimension, it dips at theta equals lambda over d. In 2 dimensions, it dips at 1.22 lambda over d. And in 3, I forget, I think it's 143 in 3 dimensions. Theta equals lambda over d. But this analysis is very, it works. So here's a homework problem for you. Do this for a rod of radius r and length L, rotationally averaged, which means you can put Q regions. You're going to have a series of different Q regions. Here's your hint. There'll be, this one's the easy one, volume squared. Then you'll come down to this length scale, and then you'll come down to this length scale. See if you can work that out. Now we've got about 15 minutes, so I'd like you to tell me if you worked out the Fourier transform of the sphere. Did anybody come up with it? What did you get? It doesn't look like I'm going to get to my slides today either. We'll definitely get to them tomorrow. So if you Fourier transform a sphere, you get the following result. Look good?
Careful with the book. I don't have the 3. Oh, I see. 3 times the power.
Yeah. I've factored out the volume. So when you just do this, the volume kind of gets mushed in with it. And so I've factored out the volume. Now, that's just the Fourier transform. Remember, the Fourier transform only gives you this, right? So to get to the intensity, obviously we square all of this. So that's the volume squared. And then you get a 9 over, oh, wait a minute, cubed. Forgot that. 9 over u to the 6th, and then this sine u minus u cosine u. squared. There we go. Now, if you play around with this formula, in the limit of u equals goes to 0, this goes to 1. No, wait a minute. What does it go to? I better be careful. Well, I'm sure it goes to a functionality with v squared. So without proving it, let's just write it down. So the intensity has a nice v squared dependence here. And then you can see, it looks like a u to the 6th. That would be a q to the inverse 6th. But as u gets big, this term dominates, and you get a square and hence a fourth. Can you see that? So let's plot this not versus q, but versus u. So this is going to round off at about u equal to 1, right, which is equivalent to this condition. Oops. And it will have an envelope, the envelope of which is 9 u to the minus 4. And then underneath it, like I say, for large u, this term disappears, this term dominates. Underneath it will be this cos squared fluctuating around like that. So that's it has a number of names. It's certainly the Fourier transform of a sphere. It's the diffraction from a sphere. It's sometimes also called the Rayleigh-Debye-Ganz limit for a sphere. Now, when there's sort of different communities that deal with this, it's also sometimes called the structure factor. So the different communities will prefer different terms. This is the light scattering community for the most part, because the light scatterers like to say this is what happens when the index of refraction approaches 1. The X-ray people like to call this the structure factor. And of course, for X-rays, most materials have an index refraction very close to 1. Fewer people, why don't I just say this, the X-ray community. Perhaps most fundamentally, though, it's just diffraction from a sphere, which is what we've been talking about for now 3 days. Diffraction, diffraction, diffraction. So any of these would work. Any questions?
So I guess visualizing the Q regions with the rod is pretty easy, right? They just line up and whatever's left on the end is what contributes. So for a sphere, I'm trying to,
The sphere is easier than the rod.
well, I'm trying to think.
Do the sphere. If you want to learn this stuff, do the sphere.
But, so for the first one, it was just when the Q region is probably around this completely, like, the shape of the sphere, like, it's the same size. But the second minimum and the third minimum, can we get that too? With the Q
You're not going to get any minima. You're only going to get these, what you could call Porrid power laws.
Just the power.
Yeah.
So in the plot we had earlier over there, so we increase Q substantially such that the Q region is increasingly smaller, comparable to the distance between the scatterers. Going to be the picture of the.
Yeah, that's an interesting question. He's pointing out I'll tuck it down here. I filled this with point scatterers, and if their separation is A, if the Q region gets even smaller, right? So if this is 1 over Q, then what happens? Well, then, okay, you're getting all these little guys, but remember, because they're different Q regions, you've got them not in any coherent phase with each other. So now the scattering will be, the total scattering will just be proportional to the number of little points you put in there. So let's sketch this. Much as the volume squared, this is n squared, correct? The number of little point scatterers. Then it's going to fall off. And then, I better be careful here, there are some subtleties, but you could see that it could come down to n.
Okay.
Now, not quite. And this is something I don't have time to teach you. If these are uniform, we still have the problem that they're all working together in some manner. Because, here's the way to say it. The uniformity implies a certain coherence between them spatially, hence a certain coherence between the phasors. And so, once again, it's only the surface that contributes. So this will actually come further down to the number of point scatterers on the surface, which is smaller than the total number. Interestingly enough now, if instead of a uniform lattice, you then perturb the lattice, you randomly move each one of these a small distance from that uniformity. When you do that, this pops up to n. Okay? And the length at which that pops up depends upon how far away you do the perturbation.
That is a problem length at which S star C occur.
Say that again?
I mean, that is a problem length for inverse Q.
Yes.
S star C.
When inverse Q can resolve the fact that you perturbed them from their perfect positions, then it will pop up to n. Yeah. Now, this is a paper we published a million years ago. I think it was 1999 in the journal Nanoparticle Research, and I can put you onto it. And that's, you might recall at the very beginning of this, I said, look, this could be just a single scatterer, or it could be an ensemble of scatterers, and it's when you start doing that, you start looking at ensembles of scatterers. And so it's a very general approach. You might say, well, I've given you some sort of esoteric only in Kansas approach. Well, yeah, true, it is only in Kansas, but it applies to a wide variety of things, and it gives you physical intuition for what's happening.
It's like crystal scattering thing. We're looking at.
Yes. Well, as a matter of fact, with the lattice, there'll be certain positions that out here that could give you peaks and so on. But let's remember, I'm only drawing the envelopes, right? I mean, here's the truth. This is what scaling analysis can give you. Other questions? Let me do one thing. Let me take 5 more minutes and just get you ready for tomorrow. some of this stuff is old. We'll talk about Rayleigh scattering. But, yeah, here we go. Here's where we're headed. This is the scattered intensity. There's that dimensionless QR. This is me scattering. Full-blown me scattering, any index refraction you can think of. You can see here I've got 3 of them, 1.1, 1.5, and 2. See that RDG up there? I'm going to have to get a laser pointer for next time because I'm not 7'3". Matter of fact, it's kind of, have you ever noticed that these whiteboards are a little too high for somebody 5'10"? So there's always this sort of vacant white area to, and some of you women who are like, 5'3", there'd be a greater gap. In any event, I digress. See the RDG in the dashed line? That's, I erased it, didn't I? That's this, okay, without the ripples. And then, as you start cranking up the index refraction, the scattering in the forward regime falls relative to, this is the scattering of the mesosphere divided by what it would be if it was a Rayleigh scatter. So actually it's weaker than it would be if it was a Rayleigh scatter. But notice, even with this parameter here that involves size and index refraction gets huge, the thing finally comes back, look at this, it touches base. Clear out here at large QR with the diffraction limit. Furthermore, other things appear. Look at this. Here's a zone with a slope of -3. What has a slope of -3? 2D diffraction. 2D diffraction starts to show up in this three-dimensional system. There's a hump that breaks away from the 2D diffraction. Comes out, like I said, it's like a runner tagging up, going around second base or something like that. Touches base and then fades away, but it touches base with the Rayleigh to bigons. There's a two-dimensional regime that we haven't understood yet. And finally, this rho prime parameter, which I'll teach you about tomorrow, a combination of size and refractive index. In each case here, there are 3 different refractive indices and 3 different sizes for each rho prime. And if the rho prime is the same, the scattering is the same. So that's why I've spent 3 whole days doing diffraction, because it's the foundation of how Rayleigh scattering and non-spherical particle scattering works. And that's what we'll do tomorrow. All right?